Before we start describing approaches to optimize the way we build algorithms, we first need to mathematically define what we mean when we say one approach is better than another. In this video, we focus on describing ways in which machine learning algorithms are evaluated. Specifically, we need to quantify what we mean by better. For our first introduction to machine learning concepts, we'll start with a boring and simple example: how to predict sex using height. As we explain machine learning step by step, this example will let us set down the first building blocks. Soon enough, we'll be attacking more interesting challenges. We use the caret-R package, which has several useful functions for building and assessing machine learning methods. We'll give more details on the caret package in a later video. For our first example, we use the height data from the DSLab package. We start by defining the outcomes and predictors like this. In this case, we have only one predictor, height, and y is clearly a categorical outcome since observed values are either male or female. We know that we will not be able to predict y very accurately based on just x because male and female average heights are not that different relative to within-group variability. But can we do better than guessing? To answer this question, we need a quantitative definition of better. Ultimately, a machine learning algorithm is evaluated on how it performs in the real world with completely new data sets. However, when developing an algorithm, we usually have a data set for which we know the outcomes, as we do with the heights data set. We know the sex of every student in our data set. Therefore, to mimic the ultimate evaluation process, we typically split the data into two parts and act as if we don't know the outcome of one of these. We stop pretending we don't know the outcome to evaluate the algorithm, but only after we're done constructing the algorithm. We refer to the group for which we know the outcome and the one we use to develop the algorithm as the training set. We refer to the group for which we pretend we don't know the outcome as the test set. A standard way of generating the training and test set is by randomly splitting the data. The caret package includes the function createDataPartition that helps us generate indices for randomly splitting the data into training and test set, like this. The argument times is used to define how many random samples of indices to return. The argument p is used to define what proportion of the data is represented by the index. And the argument list is used to decide if we want the indices returned as a list or not. We can use the results of the createDataPartition function call to define the training and test set like this. We will now develop an algorithm using only the training set. And once we're done developing the algorithm, we will freeze it and evaluate it on the test set. The simplest way to evaluate the algorithm when the outcomes are categorical is by simply reporting the proportion of cases that were correctly predicted in the test set. This metric is usually referred to as overall accuracy. To demonstrate the use of overall accuracy, we will build two competing algorithms and compare them. Let's start by developing the simplest possible machine learning algorithm, guessing the outcome. We can write this code to do that. Note that we're completely ignoring the predictor and simply guessing the sex. The overall accuracy is simply defined as the overall proportion that is predicted correctly, which we can calculate like this. Not surprisingly, our accuracy is about 50%. We're guessing. Now, can we do better? Exploratory data analysis suggests we can because, on average, males are slightly taller than females. We can see that by just typing this code. But how do we make use of this insight? Let's try another simple approach. Predict male if height is within 2 standard deviations from the average male height. So if height is bigger than 62, we will predict male, otherwise female. You can use this code to do that. The accuracy goes up from 0.5 with our previous guessing algorithm to about 80%. You can see it here. But can we do even better? In the example that we just saw, we use a cutoff of 62. But can we examine the accuracy obtained for other cutoffs and then pick the value that provides the best result? Now, remember, it is important that we optimize the cutoff using only the training set. The test set is only for evaluation. Although for this simplistic example, it does not make much of a difference, later we will learn that evaluating an algorithm on the training set can lead to overfitting for more complex approaches. This often leads to over-optimistic assessments. Okay, so let's try to build this algorithm. We will optimize our approach by examining the accuracy of 10 different cutoffs and picking the one yielding the best result. We can write this code to do that. We can then make a plot showing the accuracy obtained for the different cutoffs. We see that the maximum accuracy achieved is about 85%, which is much higher than 50%. The selected cutoff that gave us this accuracy was 64. We can find it this way. We can now test this cutoff on our test set to make sure our accuracy is not overly optimistic. We find that we get an 80% accuracy. We see that our accuracy is a bit lower than the accuracy observed on the training set, but it's still better than guessing. Now, because we tested on a data set that we did not train on, we know that our result, our 80% result, is not due to cherry picking a good result. This is what we refer to as overtraining. We will learn much more about this in future videos.